All right, welcome back to our last lesson for second semester calculus. We're going to continue with the power series. We have a very specific type of power series called Taylor series. And a Taylor series looks exactly like our regular power series, except we're going to get a little twist on it. You see the name Maclaurin as well. That has a very specific meaning. Please note that our function, our generic power series that we have here, is centered at A. Now, when A equals 0, then we call it a Maclaurin, meaning it's a specific type of Taylor series. But what we're going to do is we're going to start taking derivatives like crazy. So if we take the first derivative, notice that's a constant. It's gone. I'm now to C1. The exponent came down. I got a 2, brought the 3 down, 4 down, and so on. Now, if I evaluate this function at A, do you see A minus A is 0? Then all of these also go to 0. That's the point. So 0, 0, 0. So we end up with that it equals C sub 1. So if we do a second derivative, we now have n times n minus 1 here, and now we're down by 2. Notice we were at C1, and that's gone now. And notice what's happening with these coefficients. This is the big deal. Do you see I have factorial in here? This is 2 factorial. This is 3 factorial. This is almost 4 factorial, and so on. And if I evaluate this at A, 0, 0, 0, all those go away, and I'm just left with the 2 times C sub 2. Third derivative, you can see it's 3 factorial in front there. 4 factorial, and you can see the factorial part building up. So if we just keep doing derivative, 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 we end up with this here. And what we have is n factorial times C sub n, if we do the nth derivative, because when we evaluated at A, remember all those parts all go to 0. And so to get C sub n, because we know C sub n is here, pardon me, n factorial. And so if I divide both sides here and here by n factorial, you can see C sub n is that over n factorial. Now, don't forget, 0 factorial is defined as 1. So we're not going to divide by 0. So we don't need to worry about that. And that brings us to our Taylor series, which is this right here. This is our theorem. Centered at A, and here is our coefficients. And as I mentioned before, when A is 0, we call it a Maclaurin series. So let's do our most basic one. Is here. Now, for these, we're going to have to do a bunch of derivatives, and I always get students who ask, how many derivatives do I need to take? You need to take the derivatives until you start seeing the pattern yourself. So if you have to do 10 derivatives, then do 10 derivatives. If you can see it after just a few derivatives, then you can stop. But if I go y equals e to the x, y prime is e to the x, y double prime is e to the x, and so on, well, I definitely can see the pattern now. And it says Maclaurin, which means x equals 0 in this case. And anything to the 0 power is going to be 1. So all these coefficients are 1. So I'm going to go to my Taylor series. E to the x is going to be, and do you see my nth derivative evaluated at 0 are going to equal 1 every time? So that's just going to be 1 times x to the n over n factorial. So this definition of e to the x, and if this was live in a class, I would have all sorts of activities where I would demonstrate to you where if we let n equal 0, n equal 1, 2, 3, 4, 5, and so on. And I have a picture on another piece here. Now, this is only part of it. We've now found a power series representation, meaning a polynomial representation of e to the x. So let's do the radius of convergence. I'm going to do the ratio test. And that's going to be x to the n plus 1 over n plus 1 factorial times n factorial over x to the n. I'm going to notice that an x to the n goes away. I'm just left with an x. And I'm going to iterate that out a little bit. So let me rewrite it. So I'm going to pull that x out. Remember, it's x factorial, or absolute value of x. And then limit as n goes to infinity. And the way I'm going to write this is n factorial over n plus 1 times n factorial. And I'm going to notice that. So what I end up with and we all know what happens there. This whole part here goes to 0. This is good for us. So our radius of convergence is infinity. This is the ideal situation. We like this. Now, we have to iterate n to infinity for it to emerge. Now, just a side note, if I wanted to know the actual value of e, meaning e to the first power, when x equals 1, you can see I'm going to end up with 1 to the n, which is just 1 over n factorial. And you can actually iterate out a few of those to see that you get it. The further out you go, the closer to 2.7 and change you get. So this is an alternative definition of E. All right, moving on. So here we have e to the x once again, and I have a graph here, and I'm hoping you know that the darkest one that hopefully that's coming out, that's actually e to the x. You can see at 0, all of these are kind of close, like a little bit of a window I can deviate away, and I can use the polynomial instead of the actual e to the x. And you can see the further out you go, the further, so even this one, this third power one, you can see it converges pretty darn quickly with it as it comes through. So we're going to do this again, but this time we're not going to center it at e. We are going to center it at, center it at 0. We're going to center it at 2 in this case. So let's find some derivatives. These are all the same. And centered at 2, that's going to give me e to the second power. So my nth derivative at 2 is going to be e squared. So what does that look like for us? Well, we have this here. Instead of 1 like we had before, we're going to have e squared. And that's going to be x minus 2, because we're centered at 2, to the n power over n factorial. And if we wanted to run the ratio test to see its radius of convergence, now you'll note I didn't write the e squared. I could have e squared up here and e squared down here. They're just going to reduce out anyway. So I didn't bother putting it in. And I'm hoping that you can see this is sort of the same as the previous one. I'm not going to write it all out. If I iterate that by 1, I get the n factorials reduce. and making my radius is again infinite, because it's always going to be less than 1. All right. Number 3, find Maclaurin series for the sine. Okay. So I want you to picture this. We are going to come up with a polynomial representation that mimics a sine wave. That's really kind of cool. Now, Maclaurin means, again, that we are centered at 0. So y is sine x, y prime, cosine x. Now, these, I'm going to do a bunch of derivatives. And I want to put out there that there's clearly patterns here, right? We see positive, positive, negative, negative. We're always dealing with sine and cosine because they're derivatives of one another and so on. The key here is what happens when we plug in x equals 0? Well, that's going to be 0. That's going to be 1. That's going to be 0. That's going to be negative 1. 0, 1, 0, negative 1, 0, and so on. So what does that mean for us? Well, let's go back to our Taylor series. And I'm going to just start writing these out. And hopefully a pattern will emerge. It will, don't worry. Can you see the plus or minus 1 as we're going through? So I'm going to write it like this. 0 times x to the 0 over 0 factorial. Remember, 0 factorial is 1 plus 1, right? That's the 1 here. X to the first power over 1 factorial plus 0 times x squared over 2 factorial plus negative 1 times x cubed over 3 factorial plus 0 times x to the 4th over 4 factorial, and so on. Now we're going to look for a pattern here. First of all, these all go to 0 because 0 times anything is 0. And you notice it's all of the even ones are going away. Maybe you remember from your trigonometry class that a sine wave is considered an odd function. And so we have odd exponents. That kind of fits. So let's try to come up with a pattern here. First of all, let's take care of the negative 1 to the n. When that's 0, that's a positive 1. When that's 1, that's a negative 1. When that's 2, and so on. So that matches. Now the exponent has to be even. And to guarantee even, 2n plus 1. Here's the reason. N is an integer. When you double an integer, that always makes it even. And when you add 1 to that, that makes it odd. And that is our sine wave. That is super cool, I think. All right, let's find its radius for convergence. Convergence. Ratio test once again. Again, I'm going to drop the negative 1 to the end because we're doing absolute value, so it shouldn't matter. Now, because I'm adding 1 to the n, I have to distribute the 2 and combine. So that's going to be x to the 2n plus 3. 3 factorial. All right, and let's break that down. That should be x to the 2n plus 1. I'm going to notice that x to the 2n, x to the 2n, I'm left with x cubed over x to the first. All of that is going to become x squared. So once again, that 3 is going to reduce with that 1 to become a 2. So that's where I get my x squared from. I'm going to break down, so 2n plus 1 factorial over, I'm going to break that down. That becomes 2n plus 3, 2n plus 2, 2n plus 1 factorial. You can see that goes away. Also, I dropped the absolute value. You can keep the absolute value, but x squared is always going to become positive with real numbers anyway. Let's go down here. And as we know, that limit very nicely goes to 0. So just like with the e to the x, the radius is infinite. Which again, I think is really, really cool. All right. So we are going to find one for cosine now. Now, if this were a regular in-person class, I would have you do this because it's very, very similar to the one I just did, sine. And so I'm going to skip a few steps here and there. So I'm going to take the derivative a few times. And so on. And again, it's Maclaurin, so that's where a equals 0. So this is going to give us 1, 0, -1, 0, and so on. And again, I'm hoping we see the same pattern as before, just going to be slightly different. This is going to be n at 0, x to the n over n factorial. And I'm just going to write a few of these out. Again, the pattern will emerge pretty quickly now that we've done the sine one. This is going to be 1 times x to the 0 over 0 factorial. Once again, 0 factorial is equal to 1 plus 0 times x to the first over 1 factorial plus -1 x to the second over 2 factorial plus 0x to the third over 3 factorial and so on. Now, what makes this one a little bit different is now all of the odd ones are turning into zeros, and we're only keeping the even ones. And we've been told that cosine is an even function, and we see further evidence of that here. So let's do this. So -1 to the n. And we do start with a +1. And now our exponents need to be even numbers. Remember, 2 times any integer is going to give us an even number. And so that's what we're looking for. Over 2n factorial, 0, 2, 4, 6, 8, and so on. Now, this is the Maclaurin series for cosine. I'm often asked, do we need the parentheses down in the bottom there? Technically, yes. If you're programming or something like that, you'll definitely need those in parentheses there. Let's look for the radius of convergence. Again, I'm going to skip a few steps here or there because it's so similar to the previous one. So again, ratio test. And here's where I'm going to skip some steps. I'm hoping you can see those are gone. I'm left with an x squared. And when I iterate that down to 2n, we end up with this. And then the 2n factorials reduce out, meaning this whole thing goes to 0. So the radius of convergence is infinite. Now, by this time, you might be thinking to yourself, are they all infinite? No, they're not. Unfortunately, it's not quite that black and white. All right. Next up, we have a Taylor series for sine again, but this time we were going to center it at a equals pi over 4. And I'm actually going to change this problem slightly. So in your notes, if you would please change this, we are going to center this. Actually, I'm going to change the function altogether. This is going to be cosine x, and we're going to center it at a equals pi. We could do pi over 4. It gets messy, and actually the space that I even have for this one wouldn't be enough. Okay, so let's do this. Y equals cosine x. Y prime is negative sine x. Double prime, negative cosine x. All right, and let's plug in pi. Cosine of pi is negative 1. Sine of pi is 0. Cosine of pi is negative 1, so that's negative negative 1, 0. Cosine of pi is negative 1, and so on. All right, so this is going to be slightly different from our previous one that we just did. Cosine x equals n equals 0 to infinity of pi, pardon me. And then x minus pi to the n over n factorial. And so I'm going to write this out a bit. This would be negative 1 x to the 0 over 0 factorial plus 0 times x to the first over 1 factorial plus 1 times x squared over 2 factorial plus 0 times x to the third over 3 factorial plus negative 1 x to the fourth over 4 factorial, and so on. All right. Now, very easily we can see where the zeros are. And what's different about this is we're starting with a negative. We're alternating, but if I start at 0, negative 1 to the 0 power is a positive 1. The first term needs to be a negative 1. So what I'm going to do is I'm going to say negative 1 to the n plus 1 power. You could do n minus 1. Both would be correct. Oh, and I didn't, each of these should be x minus pi, x minus pi, x minus pi. So I should x minus pi, minus pi, minus pi, and so on. Giving us x minus pi, now to an even exponent, so that's going to be to the 2n all over 2n factorial. And so here is a second power series representation, but this time we're centered at pi. So you can see they look similar, but just different enough. It's shifted, as it were. And let's find the radius of convergence. Actually, it's going to end up being exactly the same as this one here. So I'm just going to state it. I'm not going to show it because that's all the same work. So the radius of convergence is once again infinite. All right. So we are going to do Taylor series. That is for the natural log. All right, here we go. So we're going to start with derivatives. And I'm going to do a few of these. And I'm hoping we start to see a pattern here. Do you see that this is factorial in the numerator? So let's write this out. So this is 3 factorial, which is 1 less than that. This is 2 factorial, which is 1 less than that, and so on. So let's write these out. So ln of x is, oh, and I should say we're evaluating all these at 2. So this is ln of 2. This is 1/2. This is -1/4. This is positive 2/8. I know that reduces, but I'm going to keep it anyway. This is going to be, and I'm going to call that 2 factorial, 1 factorial, and 0 factorial. This is -3 factorial over 16, and so on. So when we start looking at these patterns here, what we're going to end up with is this here. Okay, and so let's start writing some of these out. At 0, we get ln of 2, x minus 2 to the 0 power over 0 factorial. Plus 1 over x, 1 over 2, pardon me. I'm going to say 1 over 2 to the first power. And that's going to give us, that's the lead, then x minus 2 to the first power over 1 factorial minus here 1 factorial over 2 squared times x minus 2 squared over 2 factorial. And do you see these factorials are exactly going to be 1 off from one another? So this next one is going to be 2 factorial over 2 to the third power over here. And x minus 2 to the third over 3 factorial. And so on. And you can see that those are opposites right there. So how do we do this? We're going to start with ln of 2, right, times 1. Plus, all right. So this is going to give us, that's 1 now. 1 there. And let's handle the -1 to the n plus 1. because it needs to be an even exponent because it's positive for this first one. And it looks like we're getting n minus 1 factorial over n factorial. And it looks like we're getting a 2 to the n power, 2 to the first, 2 to the second, and so on. And then all that times x minus 2 to the n power. So now we have to clean that up. So we're saying that ln of x centered at 2 is going to look like this. Ln of 2 plus summation n equals 1 to infinity. Negative 1 to the n plus 1. X minus 2 to the n. Now, this, I'll just write it out real quick, n minus 1 factorial over n factorial gives me that. So actually in the denominator, I'm left with just n times 2 to the n. That one is messy. All right, let's find the radius of convergence. I'm only going to do it on this. I don't need the ln of 2. That's a constant, which is irrelevant. So let's do this. That is going to give me x minus 2 on the outside. You can see there's one more up there, so I pulled it out with the absolute value. I'm also going to get a 2 in the denominator. That's going to leave me with n over n plus 1. Which this limit goes to 1. So what we need is this to be convergent. Push that up a little. And adding a 2 is going to give me 0 to 4. So they're not looking for the interval of convergent, which is fine. So I don't have to test the endpoints, but I would need to do that if I need the interval. But in this case, 0, 4, we're centered at 2. That makes my radius 2. There it is. That one's the messiest, one of the messier ones that we're going to be managing today. For the last example, I'm not going to get really deeply into this. I'm just going to sort of show you the start of it and then show you the conclusion. We don't need to know all the gory details. This is the beginning of something called the binomial series. There's more on it in your textbook if you wanted to look at that, but we're going to start with, it's Maclaurin, so we're centered at 0, which is nice. And you can see we sort of have factorials going on here. There's, again, it gets quite complicated. Actually, it's the other way around. Yeah, k choose n, sorry. So k choose n is defined as k factorial over k minus n factorial times n factorial. And again, without getting too in depth with this, you can kind of see this is forming into that-ish. And so what I want to do is I want to jump to what this is going to look like. And it's going to look all the way down to this. So another way to write this is going to be like this. And you can see the k, k minus 1, and so on. And that goes down to k minus n minus 1 is how all of that breaks down, all over n factorial. That's taking those two, and that turns into that. So what do we end up with? We end up with 1 plus x to the k is going to give us k choose n, x to the n. And I'm not going to go too much more on that. We're not even going to find the radius of convergence, but I do want to mention this in case your teacher does expect you to have seen this before. And that is Taylor Maclaurin series. It's been a pleasure making these videos. Thank you very much.